We're going to start our inverter demonstration by showing a black start where there is no grid power to the house and the inverter is turned on. On the screen here you can see the yellow trace, that is the inverter voltage, and underneath that there is a blue trace which is the inverter current. Once I turn the inverter on, it will bring its output up to 230 volts for 10 seconds to power the grid interface, and the grid interface will check to see whether there is any voltage coming in on the grid connection. When it finds there isn't, the inverter will quickly turn its output down, connect the inverter through to the house circuits, then ramp the voltage up again. So we now have 230 volts, pure sine wave coming out of the inverter. And now we are powering the house. The inverter is acting as a low impedance voltage source. If we turn some loads on, we'll draw current out of the inverter. That's 2.4 kilowatts being drawn out of the inverter now. Next we'll try going to grid connect. I'll turn the grid on. You can now see the pink trace is the grid voltage and the green trace is the grid current. That's the current going into or out of the house. The grid voltage has the characteristic flat top that caused by a lot of electronic loads. That's characteristic of all grids now. And you can see also it's not synchronized with the inverter. The inverter is running at very close to 50 Hertz and the grid is just slowly drifting backwards and forwards. After a minute, which is a time set by a lot of grid connect regulations, the inverter will synchronize itself with the grid and connect to the grid. The inverter is now grid connected. You can see the two voltages are in phase and the grid voltage now has the flat top, which means it's directly connected to the grid. The system's set up at the moment to null the house current, so that if a load is turned on in the house, the current to supply that should come from the inverter and the grid current should remain at zero. And if we simulate some PV generation, then the current from that should go through the inverter into the battery and none of it should go out to the grid. So we'll start by turning on a few loads. As you turn the loads on, instantaneously they'll be supplied by the grid, but very quickly the control loop will bring the inverter up so that it's supplying the load. So we'll bring up the load in a few steps and you'll see how quickly the inverter controls the load to keep the current from the grid at zero. So now that is 2.4 kilowatts being supplied by the inverter and none of it coming in from the grid. The inverter, as soon as it grid connected, it became a high impedance current source. So it is driving close to a sine wave there, apart from a small deviation due to the flat top of the grid voltage. I'll now turn the loads down to zero. And as the loads step down, for an instant current is fed back out to the grid, but the control loop very quickly turns the inverter output down so that there is again no current going out to the grid after a very short time. Now I'll turn on the PV generation. So this is simulating current coming in from a PV system. Again, the control loop has controlled things, so none of it is going out to the grid. It's now all going through the inverter into the battery. And because it's going the opposite way through the inverter, the current in the inverter is opposite to the voltage. That means that power is passing from the AC side through to the DC side of the inverter. Okay, I now have a load on the house circuit again, being supplied by the inverter. I'm going to turn the grid off and the inverter will immediately switch from high impedance current sourcing to a low impedance voltage source and maintain the power on the house circuits. Okay, that's the transition into standalone mode. The inverter voltage is now a nice clean sine wave again, and the current being drawn by the loads is also a clean sine wave.